Okay, now we'd like to talk about the characteristics of the exponential function with regard to domain and range. Now remember, part of our definition of an exponential function was that x could be any real number. Therefore, its domain is going to be all real numbers. And its range is going to be y is greater than 0, okay, unless we do some sort of transformation to it. Now, let's talk about the value of the base and its effect on the direction of the function. Now, recall if my base was greater than 1, then my function increases. And if my base was less than 1, then my function decreases. Way back when, in the last unit or so, we talked about the basic function of transformations and how that works for all functions. And I would like to show you how this applies directly to the exponential function. Now, recall here we have our basic function is g of x equals a times f of b of x minus c plus d. And remember that a controls vertical stretch or compression. So now if a is greater than 1, we're going to see vertical stretch. If a is less than 1 and greater than 0, we're going to see vertical compression. So let's see some examples of what this would look like in a exponential form. So how about looking at the basic function of y equals 2 to the x. And a, in this case, would be 1. It's a little invisible one, but that's okay. How about if we took y equals 3 times 2 to the x? Well, that 3 there would indicate that we were going to have some vertical stretch going on because it's greater than 1. Vertical compression might look like y equals 1/3 times 2 to the x, where our a value of 1/3 would indicate vertical compression. Now let's take a look at what this is going to look like in actual functions. And I've graphed these functions for you so that you can see them. And we're going to zoom in right here to this graph. And we can see that 2 to the x is this blue function here. Okay, this is our basic function. Now if we change our value of a to 3, and we expected vertical stretch, we can see that in fact it is vertically stretched. The value that used to be 1 here is now 3 instead. And 1/3 times 2 to the x, represented as 2 to the x over 3 here, actually has a value of 1/3 for what used to be a value of 1. And so you can see it being definitely vertically compressed. Now, it's interesting to note when you look at this zoomed out from -10 to +10, as we show on the graph down here on the bottom, that it's a little bit more difficult to see that because it kind of looks like it's moving right or left. But don't let that confuse you. That's why we did the zoomed in version for this. Now let's look at what B controls. Now B controls horizontal stretch and compression. And if B is greater than 1, we're going to see horizontal compression. Remember, the things on the inside here are going to be backwards from what we would expect. And if B is less than 1 and greater than 0, we expect to see horizontal stretch. Now, looking at our basic function of y equals 2 to the x, where b is 1 here again, we could see horizontal compression with y equals 2 to the 2x, and vertical stretch with y equals 2 to the 1/2 x. Now I've graphed these so that you can see them. So 2 to the x is this blue function here again. And 2 to the 2x, we expected to see, because that's greater than 1, some horizontal compression. Now it's pretty difficult to see with this being horizontally compressed, but you can see that it's moving over to the left, okay? So 2 to the 2x is this red curve here, where 2 to the 1/2 x being stretched out this way would be horizontal stretch. And it's more easy to see, it's easier to see if we actually look at this version here, where we can actually see 2 to the 2x being horizontally compressed and horizontally stretched with 2 to the 1/2 x, okay, as compared to our basic function here. Now let's look at what C controls. And remember that C controls horizontal translation. So if C is greater than 0, we are going to see movement to the right. Oh, I should have put 0 here. And if C is less than 0, we are going to see movement to the left. Okay. Now remember, we're dealing with a negative C up here. Okay, so our value for C is not going to be what it looks like here. So remember how to identify C. If I have, let's see, on our basic function y equals 2 to the x, where C is 0 here, versus y equals 2 to the x minus 1, and here C equals positive 1. So we expect to see movement to the right. And y equals 2 to the x plus 1, where C equals negative 1 here. We expect to see movement to the left. So let's look at what that looks like graphed out. Okay, now again, in the zoomed in version, it's pretty difficult to see right or left. So we're going to look at a zoomed out version so that we can see right or left movement here. So our basic function again is 2 to the x, this blue function. And then we have 2 to the x minus 1, where C is positive, moving it right, and 2 to the x plus 1, where C is negative, moving it left. Let's look at the value of D. Remember, D controls vertical translation, vertical movement up or down. So if D is greater than 0, we're going to see our function move up. Less than 0, we're going to see it move down. Looking at this basic function of y equals 2 to the x again, if we had y equals 2 to the x plus 10, it would move up 10, and y equals 2 to the x minus 10 would move it down 10. So let's see what that looks like graphed out. And here, in the zoomed out version, it's very difficult to see given the scale. We have a scale here of 100, from 0 to 100 in ½ inch or less. So we actually look at the zoomed in version more easily with this. And you can see our basic function of y equals 2 to the x is still in blue. And 2 to the x plus 10 moves it up 10. 2 to the x minus 10 moves it down 10. You can see, so our y-intercept, which normally is 1 for an exponential function at 0, because anything to the 0 power is 1, gives us an automatic y-intercept of 1, unless we translate it up or down, like this, okay, or right or left. So in this case, our new y-intercept becomes 11 for 2 to the x plus 10, and for 2 to the x minus 10, our y-intercept is negative 9. Now let's talk about the natural base. Natural base E. E is an irrational number. It's kind of a cousin to pi. It only has nothing to do with pi. It's just they're both irrational numbers. And remember, the definition of irrational numbers are numbers that cannot be expressed as the ratio of two integers, and numbers like that are indicated by decimals that do not repeat and do not end. Okay, so this is approximately equal to 2.71828, and it just keeps on going. Now e can be the base of an exponential function, and that function would be e to the x. F of x equals e to the x. And this is called the natural exponential function. So we can use an e to the x key on the scientific calculator to find the values of e to the x. And if we put e to the negative 2 into our calculator, we get 0.1353. E to the negative 1 is 0.3679. E to the 0 is 1. E to the 1 is 2.7183. Ooh, that looks bad. 7183. And e squared is 7.3891. And when we graph this all out, we get just another exponential function. Okay? And we can see that it increases very, very rapidly. Okay? Here's from negative 3 to positive 3, and it goes up, clear up to 21 or so. Again, our y-intercept is 1. But if we graph it from negative 15 to positive 15, we can see it increases so rapidly that its value is nearly 300,000 by the time it gets to 15, e to the 15th power. Okay? So, that's your lesson in exponential growth.